When you first learned to program, you were told that variables are abstractions for memory cells. So if there is an int x equal to 5, then it means that a binary representation of 5 is stored in memory somewhere. Of course, once you start writing assembly programs, you realize that much data actually gets manipulated by first moving it into a CPU register before performing any calculations on it. At the machine code level, both the CPU registers and the memory are visible to the programmer. However, there is a third type of storage between the CPU and the memory, known as cache. Cache is vital to the efficient operation of modern computers. It sits between memory and the CPU and is very close to the CPU, often on the actual chip. Whenever data from memory is needed, a request is made to read the data from memory into the CPU. That's within the user program. However, it is actually copied into the cache first. From here, it is read from the cache into the CPU. The benefit of this comes from the fact that cache access is much faster than CPU access. So if we keep the memory contents in the cache, then subsequent reads can retrieve data from the cache instead of from memory. Now I've just incremented the value that is in the register AL. So this is 6 instead of 5. I'm going to copy that back, but writing back to memory is also quite expensive. So instead of writing it all the way back to memory, I will only write it back to the cache. It is not uncommon for a variable's value to change many times within a short period of time, such as with accumulator variables or loop variables. So it would be very wasteful to repeatedly copy those changes all the way back to memory. Instead, we simply copy them to the cache, and eventually, when we no longer need this variable anymore, we can later copy its value back to memory. This would typically happen at a point when the value of that variable is no longer being used in any registers in the CPU. It is therefore wasting space in the cache and gets copied back to memory right before being eliminated from the cache. Details of how and when this occurs will be discussed in a later video, but there are various approaches for handling this, and different solutions have been tried over the years. In addition, it's worth pointing out that having modified data in the cache that is not in memory can occasionally lead to coherency problems. This is especially important in modern multi-core systems where various different CPUs are trying to access the memory. Special protocols are needed to handle this possible incoherence of the memory contents. Although cache is fast, it is also more expensive than standard memory, both because of the type of hardware that is used to implement cache memory and because of the fact that it must be stored tightly packed close to the CPU, where there is limited space. Therefore, it is very common for modern systems to have multiple levels of cache. This system has 3 levels of cache. Near the CPU, we have the smallest level 1 cache. This would typically be directly on the chip, very close to the registers. Then there is a level 2 cache, which could be on the chip or off of it, but is close to the L1 cache. It will be slightly larger than L1 and only slightly slower, but still faster but smaller than the L3 cache, which would typically be located off the chip but still close to it, and much more so than memory. The memory itself would be accessed via the system bus. One final point that I'll clarify about cache memory before ending this video is that it does not read in individual memory words one at a time as indicated in the previous example. Rather, memory is divided into blocks. Each of these numbers corresponds to a memory word, and we will have k memory words inhabiting every individual block. So these k words here are part of block 0. Whenever a portion of memory is read into the cache, we read in an entire memory block all at once. So if we were to read block 0 into the cache, one place we could put it would be here on line 0. So the cache is organized into C number of lines. So here's line 0. We're reading in block 0 into line 0. This portion of the line corresponds to this memory word. This portion of the line corresponds to this memory word, and so on until the k-1 word, which is the kth word, comes from this portion of memory. Now you'll also see that there's an additional portion of the cache off to the side, and so this area is for tags. So individual line tags help the cache determine where the data in the line actually came from in memory. But the details of that depend on what type of cache you're using. The reason that a whole memory block is read in at once is for efficiency. A single large read operation is cheaper than many small read operations. Additionally, if any one of these memory words is accessed in a program, it is highly likely that another one will need to be accessed in the near future. This is known as the principle of locality, and indicates that when one memory location is accessed, then other nearby memory locations will likely be accessed in the near future. Therefore, by exploiting common patterns present in typical computer programs, we can preemptively load memory data into the cache before it is needed, thus saving time.